Hey everyone, this is Pranav here. I'm an engineer at Meta Reality Labs, also a technical lead here on driving some of the efforts here. Today I'm going to be talking about building real-time AR experiences at scale on constrained devices. So I'm going to be defining first some concrete use cases around AR experiences which are real-time. And then I'm going to be talking about how do you actually build these experiences at scale. And then finally focusing on some of the definitions of constrained devices and the context within which we are talking about building real-time AR experiences. So let's get started. So for the agenda today, I'm going to be talking about some use cases which pertain to real-time AR scenarios. Then I'm going to be talking about the constrained devices, the definition of that, and understanding some of the properties around it. Then I'm going to be introducing Meta Spark as a distributed platform, which allows us to power some of these real-time AR experiences. And then I'm going to be talking about an architectural construct, which allows us to build these real-time experiences at scale. And then finally go into the nuances of key challenges and trade-offs which exist in this architecture space. And it's going to be a very interesting discussion. But first, let's actually introduce what these real-time AR experiences are, understand these use cases, and get into the details of how you can actually build these use cases at scale on these constrained devices. But before we do that, let's actually introduce what augmented reality is. So augmented reality is the technology that overlays digital assets, computer-generated images, virtual objects into the real world space. So as you could see in this image, a person wearing like a mixed reality or AR headset is interacting with a virtual object, applying some transformations, or even anchoring those at different geolocations and sharing that with friends for a more sort of appealing AR experience. So ultimately, AR is the tech which is behind how do you sort of blend these virtual objects into the real world space and then be able to make more informative, more appealing, more helpful experiences and share it as well with your loved ones. So let's introduce some of the top real-time AR use cases. So number one is around collaboration. So as the DNA of the company stands around bringing communities together, building that social presence, bringing people together, like essentially it's the people. So one of the core use cases we want to focus upon is to actually have a collaboration model in real time in augmented reality space where people can choose to represent themselves via avatars. So avatars, as Mark Zuckerberg spoke about in the Connect event, it was more focused around the different representations which a human could choose based independent of how they look, how they want to represent themselves in an actual like sort of collaborative setting. So there are different sort of avatars which people could choose to represent themselves. And it could be as simple as a cartoonish version, which is like a stylized avatar, or it could be a more photorealistic version, which we call as like photorealistic avatar. So Mark Zuckerberg actually highlighted some of those things, and I'm just reiterating some of those avatars use cases around real-time AR scenarios. Next, we talk about shared AR calling experiences. So imagine when you are calling somebody today on your mobile devices, you are in a video calling session. So they can see you, you can see them. But when you're physically distant, you do not feel that sort of presence of that person next to you. So how can we take that interactive model for video calling to the next level where you can actually feel the presence of the person being in the same physical space as you? So this is where shared AR calling experiences come in. So as you can see in this picture, like as you wanted to connect to another person who could be a family member or friend, they could actually have their avatar representation be sort of teleported to your physical space and having that sort of an interaction model, which is seamless and makes you feel more present with your loved ones. So this is the kind of shared AR real-time scenario which we are going to focus upon and understand how we could like build architectures for this sort of a scenario and cater to the low latency SLAs which may exist. Next, we're going to be focusing on use cases around GAN-based real-time AR experiences. GAN stands for Generative Adversarial Networks. These are computationally expensive ML models. In this slide here, I focus upon two different kind of GAN use cases. One is the Smile GAN, which allows you to generate a smile on user's face. The other is the Cartoon GAN, which allows you to generate a cartoonish representation in different flavors for a given person. So for a Cartoon GAN, that's me whose image has been generated, and different sort of cartoonish representations are available. But the interesting part is that all of these capabilities here are computationally super expensive. That means it takes on the order of magnitude a few seconds to generate one representation, which would not pertain to a real-time low latency scenario. For a calling session where you want those avatars to be generated in real time, when you want these experiences to be available to you in real time, which means ultra low latency SLAs, probably under 200 milliseconds or so. How do you experience, or how do you foster to this sort of a pipeline which allows you to generate and render this content in an ultra low latency fashion? So we're going to like talk about an architecture which allows us to build such experiences. So just to summarize what we've seen so far, the properties of such real-time AR experiences, they are computationally expensive. They could require a GPU to sort of speeden up the ML processing. This could involve body tracking, eye tracking. Recently, we added like legs tracking support as well. So these are all essentially ML models or neural networks which need to run in real time at a certain frame rate and be able to like pertain to the low latency SLAs. And this is exactly where GPUs can make the hardware acceleration available and our experience more performant efficient. Also, not just for ML, that could also be required for GPUs for faster, immersive, high fidelity 3D rendering. Because ultimately, we are talking about avatars or a digital representation of a human being in 3D space. So, to do that rendering in real time in a certain sort of fidelity, you need to be able to have that done through GPUs for a better performance and graphics. Also, we need low latency. I think I briefly hinted around 200 milliseconds, sort of like an SLA. It could, of course, vary on a case to case basis. But usually, when I am in a calling scenario with somebody and I make certain kind of actions or head movements, I want those to be reflected to the other person in real time. So, that real time connotation could be debatable, but usually we expect that SLA to be as low as possible. Imagine that I make a head movement and that gets reflected on the recipient after like a second of delay. So, that is going to be not so appealing as an experience. So we want those experiences to be low latency. And from our experimentation, we think like under 200 milliseconds is plausible, where the human eye is not able to detect certain movements in real time. And hence, we want those SLAs to be as low as possible. Similarly, the quality or the fidelity of the experience, we want those to be at least above a certain resolution. And we think above 720p is a good sort of benchmark, but anything above that is going to make the experience more appealing, more high quality. And operating at 30 FPS plus is definitely like one of our goals here. Next, let's define the constraint devices in the context of building real-time AR experiences. So we spoke about building such experiences which require some computationally expensive ML capabilities, which means that these capabilities require certain compute envelope to be available on device. But we are talking in the context of constrained devices which do not have such computationally expensive sort of envelopes available so that they can power such experiences. They have strict power and thermal envelopes. That means like they have a certain power budget for a certain amount of processes or tasks which could run on device. Next, they have limited CPU and GPU capability. For example, Meta's Quest can do a bunch of things on device, and it has a very good processor powered by Snapdragon. Then it has GPU compute available on the device as well. But there's a limitation to that as well. So if we were to talk about such experiences at scale where hundreds of these avatars or potentially a lot of these users are collaborating in a real-time scenario, can the on-device compute be enough to sort of do the high fidelity rendering and ML inferencing on the device itself? We'll have to see, but looks like it's going to be very critical and tough, especially as we reduce the surface area of the compute which is available on device and move towards more sort of like lightweight or thin client form factors like AR glasses. It becomes even more challenging. So that raises or poses a very important question, that if the on-device compute envelope is limited and there's a strict power and thermal budget, then how do we run these experiences at scale on such constrained devices? I briefly spoke about Meta's Quest having some on-device compute in the form of CPU and GPU, but is it good enough to foster to like hundreds of avatars collaborating in a real-world scenario? What about like you also wanted to support higher concurrency? It becomes very challenging and tough to have the on-device compute cater to such experiences. So we have to take a step back and rethink of the architecture which allows us to cater to the lower latency SLAs and also be adhering to the performance and scalability aspects of the overall architecture. That brings us to a very important entity, and we call it Metaspark. So I'm going to introduce what Metaspark is and how that plays a significant role in building the platform for fostering and catering real-time experiences for AR on constrained devices. So Metaspark is Meta's distributed AR platform. The core meat of Metaspark's technology is its AR engine. It's a cross-platform engine which is having 3D rendering capabilities. It has a JavaScript runtime. It also has PyTorch runtime support where it can run CVML algorithms or PyTorch models. Not just that, but it also has the ability to run CUDA runtime models natively on Linux environment. Essentially, Metaspark is Meta's distributed platform, which has a publishing workflow, a distribution workflow, and the core AR engine rendering capabilities. So far, Metaspark was available as an ecosystem on device, which means it was powering AR experiences on family of apps like Instagram, Facebook Messenger, even Meta Portal. And we have a huge community of 1P and 3P users who are able to create AR content or AR effects using Meta Spark Studio and then be able to publish that onto Meta's backend. And then we have a distribution pipeline which allows to distribute or deliver this AR content to billions of iOS and Android devices. So we took this AR engine entity and tried to make it portable to the server side where we can run these models or some of our graphics workloads on the server side with higher fidelity and scale that experience to multiple users or potentially millions of avatars. So let's see how Metaspark can actually open up the doors for creating that opportunity for a bunch of use cases we spoke about here. So like I mentioned, Metaspark is our distributed AR platform. It's essentially present on family of apps, namely Instagram, Facebook Messenger, Meta Portal. FP Lite is the light version of Facebook app, which has the rendering done on the server side. So this is an interesting bit and essentially the model we're going to leverage for powering some of our real-time experiences, but in a different paradigm, which I'm going to talk about briefly. So now that we have understood the context of Metaspark as a distributed AR platform with the core meat coming from AR Engine, and we have learned about some of the use cases around real-time AR experiences, now how do we sort of bring the real-time aspect on constrained devices and then be able to create a scalable experience? So let's get into that. So just a pictorial representation of a bunch of use cases happening here. People sitting in their offices, collaborating with a bunch of peers in the AR space, doing whiteboarding, collaborating on sticky notes and whatnot in the form of like virtual objects. So when you want to like talk about scale, you want to make sure that your system or your server can actually handle multiple concurrent avatars or digital users and then be allow them to synchronize state or perform any sort of write operations and then synchronize that across multiple users if there is a stateful operation. Or if there's a stateless one, then you want to make sure that you are still pertaining to the low latency SLAs. So let's try to understand how would we achieve all of these system quality attributes and understand the trade-offs around it. So that brings us to a very important paradigm, which we call as Metaspark and edge compute. We introduced Metaspark as a distributed Spark AR platform. Let me introduce edge compute, and then let's understand how do we marry these two technology stacks together and open up n number of possibilities to power AR experiences at scale. So in this slide, I talk about 10,000 feet view of the edge computing architecture. But before we go into the details and nuances of the overall architecture, let me introduce to you what edge compute actually means. So edge compute is traditionally like cloud compute, but in this case, we are bringing the compute closer to the user. In this diagram specifically, the yellow clouds highlight the edge servers. They are like mini data centers, but have compute and caching capabilities and are much more cost effective, which you can build with lesser amount of money which you would have to put in as against a full-fledged data center. Just to throw some numbers, Meta has almost 10 data centers distributed across the entire globe, while there are a bunch more edge servers, probably in the order of few hundreds, distributed across the globe. Traditionally, an edge server is a mini data center with some compute and caching capabilities. It could also have GPUs to sort of bump up the compute latency, as in from the performance perspective. And then they're also more closer to the user, where a user can actually offload data and have the computation done right at the edge of the network. So that means it is solving a very critical problem of bringing the latency down to a much lower value. So if you were to talk about just ping latencies for a client in West Coast, hitting a data center versus an edge server, there is at least going to be a huge difference in terms of the performance gains you would see. So let's try to understand the scenario here in which two users who are geographically distributed, one happens to be in the West Coast in the US and another user happens to be in the East Coast in the US, how they are engaged in a calling scenario and connected via this edge compute paradigm. So here we have two users. One user who is the initiator of the call, who's in the West Coast, has a wearable device which is compute constrained or is a constrained device. So that means it has to offload the compute to its nearby edge server. Similarly, on the right hand side, we have another user who's the recipient of the call and has another like wearable device, which is a constrained device. It could be also a low end mobile device and needs to offload the compute to its nearby edge server. So essentially, the two users are first able to discover the nearby edge servers. It could be based on a simple discovery mechanism or algorithm, which could be based on least latency, or it could be as complex, which takes into account network bandwidth, network congestion, the time of the day at which the request was sent, and so on and so forth. So assuming that you have a discovery mechanism, once the user is able to connect to the edge server, it can start streaming some frames. These frames could be RGB frames, or it could be like even some latent codes where the edge server, which receives that data, it can process that and generate like a 3D representation. Once that 3D representation has been generated via ML inferencing, that can be serialized and sent over the wire to the receiving side edge server, which can composite the final rendered view and stream the content down to the receiver side. Now, the question is how the network backbone is set up between the two edge servers is still like questionable. You could do potentially two things here. One is edge server 1 talks to edge server 2 directly, like a P2P connection, or it could go through a centralized system, which could be more sort of feasible for more scalability reasons. Imagine that if you were to scale this architecture to group calls where you have, let's say, hundreds of participants, you would ideally want to avoid like a mesh between multiple edge servers, but rather have some sort of a relay or proxy which can take in like multiple streams and composite the final stream which needs to be received by individual recipient in a calling scenario. So once a user initiates the call, it discovers its nearby edge server. It sends the data to the nearby edge server for some ML inferencing and render. It generates the avatar, sends the data to the receiver side gets the data, generates the composited view, and streams the final composited view down to the final recipient's device, where it gets reprojected and gets displayed onto the display panel. So similarly, since it's a one-to-one call, you would expect the similar workflow from the receiver back to the initiator. And that's how you could like have like a calling scenario. Now, the interesting bit here is that because some of these workloads are computationally expensive and cannot run on device, we have to leverage the power of the GPUs on the edge servers, which allows us to generate these representations in a very low latency fashion. So once we are able to do that, and given that the uplink bit rates are much lower than the downlink bit rates, we are able to optimize on the uplink bandwidth by bringing the compute closer to the user in the form of the edge server 1. And once that generates that avatar representation, we are able to compress that and serialize it in a way so that it consumes much lesser bit rates over the downlink, and then be able to stream that content down from edge server 2 down to the recipient device. So in a way, edge compute architecture with Spark deployments on these edge servers is opening up the doors to provide a self-serve ML platform. And in addition to that, it allows us to like have the rendering capabilities on the server side. And because it's server side, we can add in any number of users and scale this architecture by having like a network backbone established between multiple servers and have them sort of talk to one another or via a centralized system. So again, sort of like repeating the quality attributes here, that why Spark or Metaspark and edge compute is the right combination to bring real-time AR experiences on constrained devices to fruition. So number one is low latency. For example, like I mentioned around the data center deployments, a typical cloud computing architecture where you have microservices deployed onto the data centers, a user could interact with one of the servers on the cloud and have the computation done on the cloud servers, but sort of in an offline scenario, or the latency SLAs might not be as aggressive as 200 milliseconds. But with edge compute, now that the compute is right at the edge of the network closest to the user, we can actually succumb to some of these SLAs which are 200 milliseconds or below and get that real-time aspect fostered and built for these AR experiences. And it is really important because the motion to photon latency, which basically means that when a person moves their head, the other user should be able to see that action and have the final output displayed onto their display panel in that low latency format, which is not possible with a data center deployment. Secondly, with the performance, like I mentioned, that we have GPUs available in the edge servers itself, which can help us perform faster ML inference. And with CUDA support and NVIDIA drivers and some of the other processes which help us like do the hardware acceleration, we can get like a higher FPS for ML inference. So it allows us to get that performance boost by having these GPUs stacked up in the edge servers. The third is the scalability. Scalability is super important, and in the context of this presentation, given that we are talking about edge servers, it is very important that you have a fleet of these edge servers deployed geographically so that you can have like a strong network backbone which allows you to connect these different servers and have them talk to one another for catering to like calling or non-calling experiences, and also have a broader reach of users so that despite the location of your user, whether they are in US, in Asia Pacific or Europe, having a presence of these edge servers will allow you to unlock these experiences for geographically distributed users, and hence scalability is really important. Awesome. So next, that brings us to what exactly happens in the edge server. I spoke about that we have the Metaspark platform, but it is essentially an AR engine which is having ML and rendering capabilities. So you still need to build a server to host that. And this is where exactly a scalable media processing framework comes into picture, which is sort of like a filtered graph-based approach like GStreamer, but allows us to build these modules in a real-time fashion where you set up the orchestration pipeline and you have Spark AR as one of those modules which can provide the ML platform and the rendering capabilities. So think of this media processing framework as like this ETL engine for RTC media, for real-time communications media, where you could like send in like some stream as an ingress, have a bunch of modules set up or filters set up for various kind of processing. It could be a WebRTC module, it could be a Metaspark module, it could be another module which applies some sort of a filter, and have that pipeline built or orchestrated, and then finally send the output of that as an egress. So together with like Metaspark and the scalable media processing framework, we are able to like solve a bunch of problems which we need to for real-time AR scenarios. On top of that, this framework is able to integrate with some of our signaling capabilities, which allows us to set up the call or orchestrate the call and discover and signal the recipients in a calling scenario where they need to join in with the other users in a group call. So essentially, like I mentioned, it's sort of like that GStreamer filter graph-based approach. You have these dynamic modules sort of plugged in into some sort of a routing policy where the data can sort of flow in and out of these modules for a particular use case. And together with Metaspark and the media processing framework, it allows us to build like a fully robust, scalable, extensible ML and render platform for pertaining to low latency SLAs for such experiences on HMDs. Next, let's talk about some of the key challenges which exist in the scalable edge compute architecture and understand the trade-offs which we need to go deeper into as an industry together to solve these and build the right tools, software, and different sort of entities to come together and solve for such experiences. So number one is the render frame rate. So typically, let's say if you open your camera operates at, let's say, 30 FPS or 60 FPS. So that's the frame rate of your device which is capturing the camera feed. Now, when you're talking about the edge compute paradigm, you're actually taking that camera feed and sending it or streaming it to the server-side endpoint. Now, the server side would be doing some sort of processing or ML computation or rendering computation, and it needs to generate that rendered output as an egress and send it either to the recipient in a calling scenario or send it back to the same client in a non-calling scenario. So this is basically what we define as the render frame rate. Basically, the time taken by the frame when it gets sent off the device to the server side, gets it processed, have the rendered output generated, and send it back to the client in a non-calling scenario. So the time taken for this entire round trip is the render frame rate. Now, you could ask that, hey, we are streaming the content at 30 FPS. Can we actually match the same 30 FPS on the receiving side? Great question. But the answer to that is it's a function of network bandwidth, it's a function of network latency, and the resolution at which you're operating at. Given that, let's say if you're operating at 720p resolution, you are actually streaming a 720p frame over the network which you're having in your, like, let's say your home. And let's say you're connected to a server which is close to your location, you may incur certain minimum latency. So it will take some minimum amount of time for that frame to be rendered back to your client, or let's say received by the recipient in a calling scenario, which can overall affect the render frame rate. So it's really hard to match the frame rate at which your client is generating the feed versus what your server can process at. In order to optimize for that, we need to have like powerful GPUs, which allows us some boost in the compute latency aspects so that we can figure out like what sort of knobs to tune and match so that we can have like a coherent experience for the frame rate which is being generated on device versus the one which is being generated on the server side for ML inference. Next is the low latency transport. I think I brought this up a few times in my previous slides that building real-time AR experiences is a challenging task. And the reason why it's challenging is because of the unreliable nature of the network. You may experience spikes, you may experience packet drops, and hence pertaining to a low latency aspect is very critical. We have had done some experimentation with WebRTC, tuning some of the knobs around jitter buffer and playout delays. It helps us get some smooth experiences, but it's still a challenge because your available network bandwidth, your proximity to the edge server can overall affect the amount of latency you would incur. So how do you sort of like choose the right transport for your stack is very critical. It could be WebRTC, it could be as another stack could like Quick or a custom transport which allows you to stream data which is relevant for your use case. All right, so for low latency transport, the next is the uplink bit rates. Like I mentioned previously, like the uplink bit rates is much lower than the downlink bit rates. So we want to make sure that as you have your edge footprint deployed, you want to make sure that edge server is more closest to the user so that you can save up on the uplink bandwidth. As you are sending the more sort of heavy data or doing some heavy lifting of the work on the edge server, you want to make sure that it's closest to the user so that you're optimizing on the uplink bandwidth and then be able to compress that data into a format which can leverage the downlink bit rates, which are much more higher than the uplink bit rates. And then finally is the smart network usage. Like for example, adhering to a better choice of compression algorithm like VPCC, or even like sort of offloading frames which actually make sense. What I mean by that is, let's say if you were having a user which is fairly static, you may not want to send every frame to the server side. You may want to like drop certain frames which do not make sense, or you may do some sort of on-device computation which generates like a similarity coefficient between similar frames and drop the ones which are not necessarily needed on the server side for computation. So these are some sort of optimizations a user could do when choosing the right transport and sending the amount of data which needs to be sent over the wire. Next is the optimization for GPU ML inference. This is a critical thing on the overall edge computing paradigm. And the reason I say that is because ultimately there's a big trade-off here. You're trying to like gain the computational latency boost by using the GPUs on the server because it's a bit more beefier machine compared to the on-device compute. So you want to make sure that you have a much more better GPU available there, but you are trading off with network latency. And the core motivation there is that with edge compute, you're trying to save on-device power and battery by offloading that compute and leveraging the GPU on the server side. But now, given that there is this network latency which you would incur, having that optimized for overall latency and experience is going to be critical when you choose the right GPU SKUs for your deployment. Then another thing is like you can also enable some sort of GPU resource sharing. Ultimately, GPUs are expensive and you want to make sure that you are properly utilizing the GPUs, your tasks are correctly allocated, and they are able to sort of reuse some of the tasks or the computation which are being done by the GPUs. So it's very, very important that you have a right workload placement optimization done and you're using the right frameworks to accelerate your inference. For example, frameworks like TensorRT or something which Meta just announced as an open source framework called AI templates are great tools to look at when optimizing for GPU ML inference. Finally, I'm going to talk about the last challenge, which is around scalable edge discovery and routing. So we talked about this one-to-one call scenario. Imagine we want to scale this up to hundreds of users. Given that we see edge server as an extension of the device, which means the device or the user doesn't know where the computation is happening, whether it's on the device or it's offloaded to a nearby server, the user is unaware of that. But we want to make sure that the system which takes care of orchestration and setting all of these edge nodes and connecting them over a network backbone is done in a performant efficient way. So imagine that based on an edge discovery mechanism, we are able to discover these edge servers, but now we want to discover multiple of these in a group call scenario. So the system which is actually orchestrating that setup needs to be smart enough that it makes the right choice of the edge discovery algorithm. Secondly, the connection which needs to exist between multiple edge nodes, whether it's via a centralized system as shown in this diagram, or it's a P2P connection between edge server is a choice which has to be made, and the trade-offs need to be deeply analyzed because each option has its own trade-off. So option one here is that each edge node connects to every other edge node and sends the data. Now, in this context, as you scale the number of users, you will grow with exponential complexity because now you're having that many number of connections which you have to manage. Versus option two, where you have a centralized system, each server is sending its stream to the centralized system where it composites it into a form where it sends it to n-1 participants. So you just brought down the complexity from an exponential to pretty much a linear one. So how do you now manage connections in both the scenarios becomes critical. Other trade-off is that now in the option two, you have to build a centralized system which understands how do you actually composite the streams together and send it to the rest of the participants. So it's a trade-off between like the number of connections which you have to manage versus like this complexity which you have to handle in a centralized system. And in addition to that, how do you incur the latency when your data is being routed through a centralized system is another thing to look at. So it becomes really critical in understanding how this distributed systems would work with the whole edge compute paradigm. But this is one of the solution spaces which people could explore in building real-time experiences at scale for constrained devices. So that is it. Thank you so much. Really encourage everyone to get involved. Reach out to us for more questions. I can be reached out at pranavs18@meta.com. Again, thank you very much for listening.